This is a very common mistake, but after watching this video, you'll be good to go. Let me show you why. So the question we have, calculate the normal force on block P. So let's go ahead and take a look at our sketch. So we have the coefficient of kinetic friction between the block P and the surface being 0.4, as we can clearly see from our question statement. So how can we calculate the normal force of block P? Let's go ahead and take a look. On block P, we have its weight pointing down. Obviously, block P and block Q are connected by string, so we're going to have the tension force pointing to the right. You will see in a second why I'm doing this. And then block P is resting on a surface. The surface will exert a force on block P, the normal force. So let's go ahead and have that. And lastly, there will be frictional force pointing in the opposite direction of the motion. In this case, it will be pointing to the left. So let's go ahead and take a look. We have the weight, the normal force, the tension, and the frictional force. So in a situation like this, how can we calculate the normal force? Clearly, the normal force is equals to the weight. So we're going to have normal force being equals to the weight. And then the weight is mass multiplied by gravity. So we have 1.25 multiplied by 9.8. The normal force is 12.25 newtons. Nothing surprising up to so far. This is our most obvious or the most simple case you can find as far as normal force is concerned. But it gets complicated when we instead want to calculate the normal force of block Q. Let me show you why I'm saying so. So on the second question, the coefficient of kinetic friction between the block Q and the surface is 0.4. Let's calculate the normal force on block Q. Let's go ahead and do that. So we're going to take the same approach. We will start with the free body diagram. The reason for that, I don't just want to give you a formula. I want to show you how it comes about. So with block Q, let's go ahead and have a free body diagram. So first things first, we need the weight, as it will always be there. And then we have the normal force, right? So this is the normal force and this is the weight. We have the tension, the friction, and the applied. So let's go ahead and have that. Okay, and then the applied force is at an angle. So there we go, we have force applied. So let me just go ahead and fill these things out. This is force applied, we have tension, and we have friction. We don't know which one is greater between the tension and the friction, but at this point, it doesn't matter. So in this situation, how are we going to calculate the normal force? Can we say that the normal force is equals to the weight? Can we say that? No, we can't, because the force applied can be resolved into components, the x component and the y component. Let me show you what I am talking about. So if we resolve F applied, we're going to have Fy and Fx. As you can clearly see, the normal force is not equal to the weight anymore. It's the normal force plus the y component of the force applied being equals to the weight. So if you actually want to calculate the normal force, you would say that the normal force is equals to the weight minus the force applied. Well, the vertical component of the force applied. So in our case, we would have the normal force being equals to the weight. So that is 2 multiplied by 9.8 minus the y component of the force applied. The force applied is 7.5 newtons. So we have 7.5. In order to find the y component, we need this angle right here. Let's assume for our situation that it is 54 degrees. So that will be 7.5 multiplied by sine of 54, right? If you want to find the y component on a horizontal plane, you use sine. And then if you want to find the y component on an inclined plane, that's where you use cos. So now it's just a matter of putting that in my calculator. 2 multiplied by 9.8 minus 7.5 sine of 54. Okay, my calculator is in degrees and not radians. The normal force that I'm getting, 13.53 newtons. So there we go. This is the formula you use when you have a force applied which is above the x-axis. The normal force will be equal to the weight minus the y component of the applied force. There we go. Let's go ahead and take a look at our third case. So in our third case, we have an inclined plane. The coefficient of kinetic friction between the container and the surface of the inclined surface is 0.75. Calculate the normal force on the 60 kg block. So we're going to apply the same technique. We're going to start with a free body diagram. Right, in the exam, you don't have to start with a free body diagram. You can just use the formulas that we are deriving here. This is just so you can have a better understanding. You can see where it is coming from. So the 60 kg block, first things first, the weight. I worry about everything else after the weight. And then we have an inclined surface. And then the normal force will be perpendicular to the surface. So this is our normal force. We have our force applied down the incline. So there we go. We have force applied. And then if force applied is down the incline, then the frictional force should be up the incline. That is not necessarily true, but in our case, it is true because force applied is down the incline and we have the parallel component of the weight also down the incline. So there is no miracle that can happen. That object is going down the incline. So here we have frictional force. This is force applied. So let's go ahead and take a look. Our normal force will be equals to what in this case? You can see that the normal force doesn't necessarily line up with the weight. So we cannot say that the normal force is equals to the weight. But we can resolve that weight into its parallel and perpendicular component. So the weight can be resolved into this right here would be weight parallel. So this is weight parallel, and then we have weight perpendicular. So in a case like this, in an inclined surface, we have the normal force being equal to the perpendicular component of the weight, of which the perpendicular component of the weight is mg cos of theta. So in this situation, we would actually, this is the formula you need to use on an inclined surface. So in this situation, we would actually have 60 multiplied by 9.8 cos of 15 degrees. So what is 60 multiplied by 9.8 multiplied by cos of 15 degrees? That is 567.96 newtons. So there we go. We have our normal force. This is the formula you have to use. So we've looked at 3 scenarios. There is one last one. Let me show you. We have to go back to this sketch. So in this sketch, here's what I'm going to change. Instead of the force applied acting above the x-axis, let's make sure that it's acting below the x-axis. Right, let me just erase that. So this is what I'm talking about. When we have a case like this, where the force applied is pointing downwards, what will be the normal force? Okay, we are still going to derive the normal force. Let me just write F applied in our new sketch and resolve it. So we have F applied somewhere here. So this is F of x, nothing changes, but what changes is F of y. F of y now points down. So we have f of y pointing down. So let me get rid of this. If f of y is pointing down, then we can say that the normal force is equals to the weight plus the y component of the applied force. So now in a case like this, you just say the normal force is equals to the weight plus the y component of the applied force. So those are the 4 scenarios you will likely come across in the exam. Maybe 2, maybe 3, maybe even 1 scenario, but you need to know what to do in these different cases. So right, this is how to calculate the normal force under Newton's laws of motion. Tell me, which video do you want me to do next? Leave a comment below and I will take care of it.